So yeah, this was slide number 17. We jumped over this. This is, if you remember, we had a separate document that had some example questions on it. We're going to, I'm looking around, I must have left my stylus in the other room. I'm going to grab that. But take a look at number 12 with me in this other document. Here it is. And we'll do the problem on the other document because there's not really any room to do it here. I can cram it over here, but we'll do it on the other one. So we have a gas phase reaction in this case. Two particles of gas react to make two different particles of gas. It says the equilibrium constant is 18. It doesn't tell us whether that's Kc or Kp. That means, if it doesn't tell us, it means implied that it's Kc. In this case, however, Kp and Kc are the same value because you have two particles of gas making two particles of gas. When your delta N of gas is 0, then Kp equals Kc. If you can remember, we talked about that a long time ago. It gives us an amount of SO2 that gets put into the reaction container first, and an amount of NO2 that gets put in it first. And you'll see that the reaction will proceed to the right and make some products. And the question is, how much of one of the products is present then in equilibrium? Good example for us to just bring this all back and remember what ice tables are and how we construct them. Give me a moment though. Grab my stylus. Okay. Before we jump over to the other document, one thing I do want to mention, they told us that 1 mole of SO2 and 2 moles of NO2 are put into this reaction container. In our ice table, we don't want to put 1 mole under that and 2 moles under that. Be aware, remember that we're going to deal with concentration here. That's the default unit. We don't ever put moles into an ice table. We're always either going to put molarity for concentration. If you're given a Kc value, use molarities in the ice table. Or if you're given a Kp, use atmospheres in your ice table. Not moles. So we're given moles here. You do see the volume of the container is given. So it's 1 mole of SO2 in a 20-liter container. So we're going to have to determine the molarity of that. Same thing for the NO2. Let's do it over here. So remember, I'll just write it up above. There was 1 mole of this and 2 moles of this put in initially. But in our ice table, we have to use molarity. So it's 1 divided by 20 ml, which is 0.05 molarity, and 2 divided by 20 liters, that was 0.1 molarity. And it also did tell us that the K value of this reaction is 18.0. So the question was, what is the SO3 concentration? Yes, it does say what concentration of SO3. So we definitely don't want to use pressures here. We want to use the concentrations of everything. That's what we're going to ask for the SO3. Okay, so this is what we're trying to find, is the equilibrium amount of SO3 that's made. Initially it was 0, but then some of it's going to be made. So both of our products are 0 initially. You can't end with 0 of anything in equilibrium. Equilibrium means you're going to have some reactants, some products present. So the reaction is going to have to go to the right. And as it does that, I don't know how much goes to the right yet. So the reactants are going to go down by some amount we'll call X. And as they do that, the products are going to go up by that amount as well. Because all the coefficients are 1s, our X terms are all the same. So at equilibrium, we have 0.05 minus X molarity of SO2, 0.1 minus X of NO2, X and X of the 2 products. All right, solve for X, that's going to be our answer. That's the concentration of SO3. So pretty easy. We're just going to call this thing K equals 18.0, and that's equal to x squared over 0.05 minus x times 0.1 minus x. Oh, and it looks like this is going to be a polynomial function that we're going to have to solve for x with. Let's evaluate the denominator. It's just going to be x squared over, we have to use the FOIL method down here, is 0.005 minus 0.15x plus x squared. On the bottom? Yes? All right, then we're going to take that denominator quantity and multiply it by 18. We eventually need to have this thing in a standard form. So yeah, 18 times that quantity in the denominator. Let's see, 18 times 0.00. I was thinking I could maybe do this from memory. 0.09, thank you. Minus, this is 2.7, right?
Yeah.
So yeah, 18 times the 0.15 is minus 2.7x, and then it's plus 18x squared. And that's equal to x squared. That numerator still it will be the last thing that's left in the on the right side when we multiply out the denominator. So put this thing into standard form, get that x squared over with the other x squared terms, and just rewriting this thing and making it the normal polynomial form. 17x squared minus 2.7x plus 0.90 equals 0. And then we're going to use our handy calculators and have it solve this quadratic for us. If we have a calculator that will do that. I will say, once you get to this point, keep in mind that on the other slide, or on the other document, this was a multiple choice question. And it turns out if you look at the answer choices that are given in the multiple choice question, there's only one appropriate answer. The other 4 of the given answers are bogus. And I'll show you why that is. Notice, looking at our ICE table on the equilibrium line, remember you can't have negative concentrations. So if x gives you a negative number, that can't exist because your products are going to be x concentration. Can't have a negative concentration. Or notice that if x is bigger than 0.05, that can't be either because the reactant concentration is 0.05 minus x. It can't be bigger than 0.05 because that'll give you a negative concentration. So if I take you over to this, look at the answer choices. They're all positive, but only one of them is less than 0.05. It's A. You can't have B, C, D, or E because they'll give you a negative concentration for the reactant. So the answer is that. Now, if you didn't catch that, you'll have to go back and use the quadratic formula. I mean, you can certainly put your A, B, and C term into the quadratic solver on the calculator, and that will give you 0.048 molarity for the answer. Any questions on that? If you're lucky. It's pretty rare that there's only one physically possible answer choice. There at least will be 2. Yes? But one of them is above 0.05, right? What are your 2 answers that it gives you? 0.048. Yeah, the 0.11 is no good because if you put 0.11 in for x here, it's going to give you a negative value. You can't have a negative concentration, even for the reaction. You have to have positive amount for everybody at equilibrium. So that's why the 0.11 is no good. And of course, it was in here as one of the answer choices. It's there. But that's a good wrong answer. From the 0.11 is yes, because 0.11 can't exist. It can't be the answer. from the teacher's perspective, it's a good wrong answer. Anything else about this one? Okay, go with me then, 2 slides forward now. We had done slide number 18 already, and we get to slide number 19. We skipped over this one, and I'd like to go over this one with you now. In fact, I'm going to give you some time to do this yourself and see how you do. Number 75 from the book is this. In a certain experiment, pure arsenic trihydride, AsH3, was put into an empty sealed flask at a pressure of 392 torr. After 48 hours, the pressure in the flask, the whole pressure, the total pressure in the flask, was observed to be constant at 488 torr. What is the equilibrium pressure of the hydrogen? So this reaction is going to happen. We start with, I'm going to go ahead and start an ice table here. So initially, there was 392 torr of the reactant and none of the products. Yes? It has to, the ice table pressures have to be in atmospheres if we're solving for K, if we're using a K value. In this problem, you end up not needing a K value, so you can leave the units in torr. If it's not obvious to you that you don't need the K, you'd want to change it to atmospheres, okay? But the problem says nothing about the K value, see that? And we don't need the K value in this thing. So I'm going to go ahead and just leave it in torr. But again, if you're not sure whether you need to find K, then you need to change it to atmospheres. Okay, one other thing about this reaction, and I'm going to admit this is really embarrassing. In my first hour class, I missed it. I hate that. I know I did. So yeah, they're very gracious. One of these products is a solid. I went ahead and filled this thing out. It was, I ended up including it in my final calculation. That was a big no-no. Only consider gases and aqueous physical states in equilibrium, any equilibrium problem. As being a solid does not matter at all. Its quantity doesn't matter. We need to know that there will be some of it in equilibrium, but that's it. We don't need any quantity of any solids or liquids. So it's gases only on this thing. Yeah, first hour, they're so nice. They're so good to me. And it's shameful. Anyway, this thing has to proceed to the right because we can't end with 0 of anything, so it's got to make some hydrogen. So as it does that, I could say the left side goes down by x, but I'm not going to. Using the coefficients on here, and that's one of the reasons I like this question, because the coefficients aren't all 1. We're going down by 2 of these and going up by 3 of these. So in my change, I don't know how much the ASH3 changes, I'm going to say it goes down by 2x. Not just x, but by 2x. And then when this goes down by 2x, this is going up by 3x. To keep our coefficients whole numbers. I could say this goes down by x, but if I did that, this would go up by 3 halves x, 3 over 2x. I don't want fraction coefficients. So I'm just going to leave whatever the coefficient is, that's how many x's I'm going to change by. So that means this, that the reactant is 392 minus 2x, and the H2 is just 3x. Now I started this thing by telling you I was going to let you do this. Now in my shame, from what happened first hour, I went ahead, I was trying to protect you from making the same mistake that I made, and I wound up doing most of it. But I want you to see in this one that you didn't end up needing a K. I mean, we haven't finished this thing yet, but you don't need a K value. Take a look at what else the problem gives us. It says, after 48 hours, the pressure in the flask was observed to be a constant 488 torr. Now, the pressure in the flask is exerted by all gases present. There is still some of the reactant present, and there's some of this product present. So the total pressure of this, P total, is 488. that would be the ASH3 that remains, which is 392 minus 2x, and then added to the hydrogen that's been produced, that's the 3x. Those are our two gases that are remaining. So add those two together. The math on this is really simple. Negative 2x and a plus 3x gives us plus x here. So 488 minus 392 is 96. X equals 96. That's not our final answer. In fact, if I go back to this multiple choice question, oh, that was, sorry, that was in the book. Yeah, this is one that was in the book. So anyway, the question is, what is the equilibrium pressure of H2? 96 is not the final answer. It's 3 times 96 that we need. So where am I at here? The pressure of H2 at equilibrium would be 3 times 96, which is 288 torr. So in this problem, it was fine to just leave it in torr because we never used a K value. If we had to use K to solve for an X term or to figure out how much of something we would have to use atmospheres. Yes?
The book, the part B asked us to solve for KP, so would we have to convert?
You would, yes, that's right. We would, it did ask for KP. You'd have to change, just go down here and change that value into torr, into atmospheres and then into atmospheres. Yes, you'd have to use the ratio in atmospheres. Yep. Everybody hear that? Anytime you find KP, use atmosphere. One more. And we're going to jump 10 slides now. I do want to mention, as we're just moving down, I'll remind you, I mentioned this before our break. If you remember, before break there was a snow day. We lost a day in chapter 13. And I had decided, Mr. Hevel and I both, talked about just putting the 5% rule off until chapter 14. We'll use the 5% rule all the time in chapter 14. It's a shortcut. You can do all the problems the way that we've learned how to do them. If you self-study the 5% rule and on the quiz you want to use it, it's fine. But any questions about, like if you see the 5% rule being used in the solutions manual or whatever, just ignore that. You can do all these problems the way that we've learned how to do it. We use it. It's a way to get out of using the quadratic formula, is all it is. But you can use the quadratic formula every time and it'll work. So I will introduce the 5% rule later. It is not necessary for doing any of the problems in chapter 13. It's just a shortcut. So we're going to skip it for right now. Go down to slide number 29. This one. This is the last example that I would like to do with you this hour. It's from the other document, so that's number 18. I'm going to take you back there. Okay, I know there's writing that kind of goes into the space of number 18. That's from the other problem. We haven't looked at this yet. Consider this reaction, another nice reaction in which we have 2 gas particles making 2 new gas particles. All the coefficients are 1s. In an equilibrium mixture of these gases at 1,000 degrees, the partial pressures are, so remember, it says an equilibrium mixture. So we can use these values to find the K value. The problem doesn't give us K, but it gives us an equilibrium mixture in which we can find the K. We'll need that. So the question is not what is K, that would be very easy, just put the numbers in, products of reactant. But here's the question. It says, from this equilibrium mixture, it says more water is injected into the equilibrium. So notice that water, as in the form of steam, is a product here. So what it's saying is more product gets injected into this reaction, and that's going to cause, by Le Chatelier's principle, that causes the reaction to shift to the left. If you add more product, it becomes product heavy, it's going to shift to the right. If you add more products, it's going to become product shift heavy and shift to the left. It tells us how much it shifts. The H2 reactant pressure goes up to 10 atmospheres. So the question is, what was the new water pressure when it finally reestablishes equilibrium? So let's take these values. I, on the other document, had gone ahead and put these into the initial line. So those are there. We have to just remember, so we don't have to flip back here. The hydrogen is going to get shifted to make more of it. There will be 10 atmospheres of it after this shift happens. So here's our initial amounts. Initially, this is just straight from the given information in the problem. Initially, and this, remember, was an equilibrium mixture. So this thing is just sitting here at equilibrium. It's not shifting left or right because it's comfortable. What is the K value according to these? K would be the products, 13.88 times 5.18 over the reactants, 5.75, and 6.25. I'm just going to squeeze that in. When you do this, that times that divided by that, and that's very simple, you're going to get 2.00. So the K value for this reaction is 2. As long as the temperature stays constant, K remains 2. Now the problem mentioned the temperature, but there was no change in the temperature. So this is a reaction that's happening at 1,000 degrees Celsius. Temperature is fixed at 1,000 degrees. It says that more water gets added. So I'm just going to say, I'm going to change the color on this so it doesn't run into the purple. More water gets added. It doesn't say how much. It just says that water gets added, causing the reaction to shift left. How do we know that it shifts left? It tells us that the hydrogen pressure goes up to 10. So at equilibrium, when this shift happens and it goes left, the hydrogen winds up being 10 atmospheres. So we don't know how much water got added to this thing, but it caused the reaction to shift to the left so that hydrogen on the left side became 10. Now that is Le Chatelier's principle. If you add more reactant, it will shift to the right. If you add more product, it will shift to the left. When more water was added, then the reaction was forced that way. Since I know how much hydrogen we started with and how much hydrogen we end with, we know what the X value is. You don't need an X term in this ice table. Starting at 6.25, going up to 10 means that the hydrogen pressure went up by 3.75 atmospheres. So we know what the change was. And if the hydrogen went up by 3.75, the CO2 had to go up by 3.75 as well. You can't make more of that without making that as well. So that went up, and that's because of the 1-to-1 ratio, 3.75. So we know how much CO2 we end up with. We started with 5.75 and 3.75. So that has gone up to 9.50. So on the right side, if the reaction shifted to the left and the reactants went up by 3.75, the CO must have gone down by 3.75. It's a 1-to-1 ratio with the other things. So that has gone down by 3.75. So 13.88 minus 3.75 gives us 10.13. Now in this process, the water also had to shift left. And so whatever amount we added of water, and it doesn't ask us how much we added of water, it asks us, the question is, what is this amount down here? How much water is there at equilibrium? Well, it did shift, and it went down by 3.75. But remember, some got added. So you can't just take 5.18 and subtract 3.75 because some water got added to cause this shift in the first place. So we don't know what that value is. That's the X term. that we have to put in this. Our change is not in terms of x because we know how much everything changed by. Our unknown is what amount of water is present in this mixture at equilibrium. Just call that x. And so, we can easily solve for x. The k value is known here, it's 2.00, and that would be the products, 10.13 times x over 9.50 times 10. Solve for x, the math turns out to be really easy. So these equilibrium problems can have lots of different variations or twists thrown in. I like this problem. I think it's important for us to do together because it has Le Chatelier's principle built into it. It has a reaction shifting. And of course, it's got us doing the stoichiometry and determining the K. It's got a lot of components to it. When you get an answer for x, here are our choices, and the answer was E, 18.8. I don't know if there are any bad answers. Like, is there anything up here that we can rule out? I don't know that there is. Yeah, no, there's no obvious wrong answer here in the choices. So yeah. Any questions on that? Okay. I'm going to leave the rest of the time this hour, almost a half hour, the better part of a half hour. If you have any questions about anything, feel free to ask, whether it was from what was shown today or in the homework exercises or anything else. This is a good time to ask. Otherwise, we're done.